Namaste bachcho, welcome to the class. So today we're going to tackle a really important topic from your second unit. That's electrostatic potential due to a point charge. Now I know the name sounds a bit heavy है ना, but बिल्कुल tension मत लो. My promise is by the end of this session you'll find it super simple, super clear, and you'll be perfectly ready for your exam. So let's start with something you've probably all tried. You run a comb through your dry hair and, like magic, it can pick up little bits of paper. Ever wonder what's actually happening there? It's not magic, of course. It's all about the invisible world of electric charges and the forces they create. And believe it or not, this simple trick is the perfect way to start our topic for today. All right, so here's our game plan. We'll start by understanding that comb trick. Then we'll use a very simple idea, climbing a hill, to get the core concept. After that, it's straight to the official NCERT formula you need for your exams. We'll see where that formula comes from, and then, the most important part, I'll show you the common mistakes that you must avoid. And finally, a quick summary to lock it all in. Jello, let's get started. So, back to the comb. When you rub it, it basically steals some electrons and gets electrically charged. This charge creates an invisible area of influence around it, what we call an electric field. It's this influence that pulls on the paper. And the strength of this influence at any single point, well, that's what we're trying to understand today as potential.
Okay, to really get a feel for what potential is, I want you to do something for me. For just a minute, forget everything about charges and electricity. Just imagine you're climbing a hill. Seriously, this one simple mental picture, it holds the entire secret to understanding electrostatic potential.
Think about it, right? If you push a heavy ball up a hill, you have to work against gravity. You're getting tired, you're using your energy. So where does that energy go? It doesn't just vanish. It gets stored inside the ball as what we call gravitational potential energy. The higher you push it, the more energy it has stored up. Simple enough. Now let's bring that idea back to our world of charges. Imagine a big positive charge, plus Q, just sitting there. Think of it as our hill. Now you bring another small positive charge, plus Q, and you try to push it closer to the big Q. What's going to happen? Well, they're both positive, so they're going to push each other away. They repel. So you have to do work against this repulsion. And just like with the ball on the hill, the work you do gets stored as electrostatic potential energy. See the connection? We're not climbing a real hill. We're climbing an electric hill. Okay, so that electric hill idea gives you the feel of the topic. But in your board exams, you need the exact, precise language from the textbook. So let's look at the official NCERT definition. This is exactly what you need to write to get those full marks. Let's read this carefully, word by word. Electrostatic potential at a point is the work done to bring a unit positive charge from infinity to that point without acceleration. Every part is important. Unit positive charge just means a charge of +1. From infinity is our reference point, our starting line. You can think of it like sea level when we measure the height of a mountain. So if that long definition feels a bit much, just boil it down to this one simple idea. Potential, which we call V, is nothing but the work done, W, for every unit of charge, Q, that you move. It's the cost of work you pay per charge. That's it. V equals W by Q. And this brings us to the hero of today's lesson, the main formula. The potential V, at some distance r away from a source charge Q. This is the formula you'll be using again and again in your numerical problems. And remember, that constant 1/4πε0 is just what we often call K to make things easier. Now look, you can just memorize this formula and solve problems. That's fine. But the best students, the ones who really understand physics, always ask, "Sir, how did we get this?" So let's quickly look at the logic. Don't be scared of the derivation, just follow the story. It's actually quite simple. It's really just a 4-step story. First, we start with something we already know, Coulomb's law, to find the force. Second, we figure out the tiny bit of work, dW, needed to move the charge a tiny distance, dr. Third, to find the total work from all the way at infinity to our point r, we use the powerful tool of integration, which is basically a way to add up all those tiny pieces of work perfectly. And fourth, when the math is done, out comes our beautiful, simple formula, V equals KQ divided by R. Let's just plug in some easy numbers to see how this works. Say we have a charge Q of 2 coulombs, and we want the potential at a distance r of 2 meters. We just use our formula, V equals KQ by R. Look, The 2 in the numerator and the 2 in the denominator just cancel out. So the potential is simply equal to K, which is 9 into 10 to the power 9 volts. Bilkul straightforward.
Okay, everyone, pay close attention now. This might be the most important part of our whole session today. I call these mistakes the silent killers because they are small, sneaky errors that can make you lose marks in your exam even if you know the topic. Let's make sure you don't fall for them. All right, listen very, very carefully. First mistake, forgetting the sign of the charge. If your charge Q is -2 coulombs, you have to put that minus sign in the formula. Potential can be positive or negative. Second, so many students mix up potential, V, with potential energy, U. Just remember, V is work per charge. U is the total energy for a specific charge. And the biggest trap of all, people try to add potentials using vectors. No! Please remember, potential is a scalar. It has no direction. If you have 3 charges, you just add their potentials arithmetically, like 2 plus 5 minus 3. That's it. It makes the math so much easier. All right, so we've understood the main idea, we've seen the formula, and we know which mistakes to avoid. Now let's just zoom out for a second, see the big picture, and then I'll give you the key points to remember for your revision. Now remember the electric field from Chapter 1? It's really interesting to compare it with potential. Look at this graph. The electric field, E, which is proportional to 1 by r squared, it drops off very, very fast as you move away. But potential, V, which is only proportional to 1 by r, falls off much more slowly, more gently. This comparison is a favorite question in exams, so please remember this graph and this relationship. Okay, Butcho, let's do a super quick summary. 5 points to lock in your brain. 1. Potential is just work done per unit charge. 2. The formula is simple. V equals Q K by R. 3, and this is the most important one, potential is a scalar quantity. Simple addition, no vectors. 4. Always use the sign of the charge Q in your calculations. And 5, potential falls as 1 over r, while the electric field falls much faster, as 1 over r squared. If you know these 5 points, you have mastered this topic. And to finish, I want to leave you with a little puzzle to think about. If we agree that potential is like an electric height, then what will we call a surface in an electric field where every single point is at the exact same height, where the potential is constant everywhere? Think about that, because your answer is the key to our very next topic. All right, that's all for today. Keep revising, and I'll see you in the next class.